welcome everyone. For this session, we're going to be revisiting the topic of exoplanet demographics. So I'd like to introduce the first speaker, the invited speaker, Adam Kraus.
Thanks, Josh. So far, we've had a lot of prescriptive advice over the course of this week. Know thy star, thy planet, thy sun, thy earth, various other things that I'm sure I've lost track of along the way. And so now we're at the point in the week where usually someone shows up to give the brief overview, adding know thy binaries. Both for knowing thy planet, they're going to be important about that, for that, as we heard yesterday, but also for learning about all the astrophysics of planet formation, in binaries and not. Okay. And so I like to start on this slide because it gives the visual demonstration that's now just a little more relevant as we're really starting to plan for like HWO of why we need to care about binaries. This is the solar neighborhood, and if you look around here, you see a lot of familiar names, and a lot of familiar names that actually are binary star systems. Alpha Centauri, Procyon is there, Sirius is there, 61 Cid, 40 Eri, I'm sure Eta Cas is around here somewhere under a GJ name. There are a lot of A's, B's, and C's on this plot, if you can really squint and see, indicating that these are binary systems. They're all over the place. The majority of solar-type stars, roughly half or a little more, are going to form in binary systems. So we want to know, do they have planets? What kind of planets? And how do they cause problems for finding planets? Just to make this a little more quantitative, we can return to some plots, some of which we've already seen this week, from Afternoon1 et al. 2022, showing the multiplicity fraction as a function of primary star mass, where for sunlight stars, it's about half. It gets even higher for the high mass stars. It drops off for lower mass stars. But it still is in the 20 to 30% range, even for M stars, and really only drops below that until when you get to like the brown dwarfs and things. And they're going to span a wide range of orbital radii. This is one of the canonical plots from Afternoon1 et al. 2010, showing the 7 major axis distribution for G-star binaries, where the peak is right around a few tens of AU. So half of the half, or a quarter, are going to be right in the middle of the action for planetary systems, and the other half, so another 25% of the total, can at least be dynamically important either for long-term survival of planets, for sculpting the mass accretion and the protoplanetary disk environment during planet formation, etc. And so this is going to be both a problem and an opportunity. The problem, at least to some extent, is that the flux from the unoccluded star can bias your planet radii and can change your demographic conclusions, as we heard yesterday in the talk from Dalen Bergston. If you have a binary there, you have two sources of flux. Only one is data occulted, so the occultation is going to be shallower. The flux dip is going to be shallower than otherwise. Depending on whether it's around the primary or the secondary, you get either a large effect or a huge effect. But also, even beyond the flux dilution, this is also going to change your assumptions about all the properties of the planet if you're using incorrect stellar parameters, or if you're not sure where it's at, or if it's changing like how your transit fits out to give you different sets of parameters. And so, as Tyndall Sullivan showed a couple of years ago, then you can move planets around quite a bit. You can start with a sample of planets that are nominally in the sort of rocky planet habitable zone and move a lot of them out. Some move upward because they're actually bigger than they appeared, but a lot move to different orbital radii, and depending on which star it's around, this can change where it is with respect to the habitable zone by quite a bit. But there are also opportunities here to understand astrophysics. I'm using the scare quotes because I've used a slide much like this before and usually called it obstacles, but let's be positive. There are opportunities. And so we can take the story of planet formation and then add the binary star system and ask, how does this change? And so at various stages, we can say, let's think about early on the accretion process. When you're building your stars, and then when you're building the disk that the planets will build out of, then you're accreting mass out of an envelope. If you have one star there, it's straightforward for certain definitions of that. The mass comes down, lands on the protoplanetary disk, and then accretes inward to the star. If you've got two, then you start raising the question of where does the mass go? Does it go to the primary or the secondary? How much of it goes there? Is this going to depend on like the specific minimum of the envelope? And it'll probably change over time. Even after you decide how much mass you've got around, which also is going to affect the binary properties themselves, then you're going to start truncating disks from the tides of the binary companions. So you're going to do things like change where the planets can form at, but also change the mass budgets that you're working with to build planets. Probably reducing them, but also maybe changing their composition. Later on from that, even once you start building up planetesimals out of this probably reduced mass budget, then the tides are going to be stirring them up, so it's going to get harder to build large planets from there. I don't know if this will prevent planet formation, but it'll certainly slow it down. You're probably going to clear the disks more quickly because the tidally open gaps are opening up the disks to photoevaporation from the other star, and also just removing the mass budget, so the whole thing will reducing the mass budget, so the whole thing will clear out more quickly. And then even if you make planets at the end of all of this, then long-term secular dynamical interactions are going to lead to some number of ejections. And these all fit nicely into a story of what happens in planet formation. So early on, when you've got just a pre-stellar core or the class 0 or class 1, you're still talking about building your star and building your protoplanetary disk, but you've already got disks around pretty early on. As you get to more of the planet forming stage, class 2, where you've got a star and a disk, but the star is largely baked in, that's when you get most of these other effects. But then ejections can last straight through past that point and through the lifetime of the system. So it's good to return first to the early stages and just remind ourselves what is seen there, because it's saying initial conditions. And early on, there was evidence that there were disks, but different ones. And so you could have planet formation, but you needed to ask, are you getting the same planet formation? And are you getting less of it, or different forms, et cetera? And so back in the 1990s, like Eric Jensen showed that if you look at the disk flux out in the millimeter, a proxy for mass sometimes, as a function of separation, then you have lower fluxes close in for close separation binaries. But then once you get to very wide ones, then you have a wider range. I'll return to a more recent version of that before long. And so he basically found that the most luminous objects were among the wider binaries and single stars, so that maybe you get fewer and less massive disks among the tighter binaries. And this got explored throughout the next sort of 15 years until Spitzer really revolutionized our ability to look more at disk demographics in much larger samples, where, for example, Lucas Cieza looked at the disk occurrence rate in binary star systems and found, oh, there's a lot of disks in the wider systems, but then the disk fraction drops once you get inside of there. And for example, I found in a uniform sample in Taurus that if you can get down to solar system scales, you basically see inside of a few tens of AU, the disk fraction drops to a third really quickly. And going to places like Ophiuchus, you see it drops to a third within less than 1 million years. Whereas outside of solar system scales, it stays high as single stars, basically for the lifetime of planet formation. And so this sets up an initial prediction that maybe close binaries aren't so great, or at least are different. And updates on the story of how much stuff you've got to work with have also been able to sort of dice up the sample more and say what is happening at different orbital radii, binary orbital radii, corresponding to changes in how influential the binary companion will be. So like Robert Harris in 2012, and then various ALMA studies since, have shown that closer binaries have lower disk fluxes in the millimeter. This can be a lower disk mass, but also ALMA has been able to spatially resolve them and show the disks are smaller. Maybe there's more efficient radial drift of the grains because the dust is moving pretty close in. And so if they're optically thick, then maybe you can hide more mass there, but then you're changing where the stuff is at in the disk. And most recently, ALMA's really been able to show us at the planet formation stage that you're getting disks sort of in surprising configurations, some of which surprise me, some of which don't, I should say. For example, alignment seems common, but in even very close binaries, like this is FO tau from Toffelmeyer et al. 2024, and then Kuchar et al. 2025 looked at DF tau, where these are binaries orbiting on solar system scales, 10 or 20 AU orbital radii. And they looked with ALMA on the longest baselines and found, oh, there are disks around both stars, so you can build planets there. Weirdly, there's no circumbinary material that can be seen. That doesn't really hold. I don't see how that can hold because the viscous timescales for the circumstellar disks to accrete should be like thousands of years. So they should not stick around unless something's feeding them. We just don't see what's feeding them. They're aligned, which initially surprised me, except dynamics maybe lead to alignment in cases like this. But I don't know what to make of the lack of the circumbinary mass reservoir, and we're starting to see in cases like DF tau B where they actually didn't know it was a disk until ALMA because there's no near-infrared excess, so there's a cleared inner gap in that disk. Maybe a sign of planet formation to echo the arguments we had for the last 15 years with transitional disks. So we've got a lot of good context from young stars, but we want to look at planetary systems as well, because a disk is not planets, and it's not necessarily easy to connect there's a disk here today to what planets you'll get 5 good years later. Fairly early on, RV surveys showed that there were fewer close binaries among RV planet hosts, which was at least highly suggestive. Though there were caveats with sample selection and whatnot, it's hard to do RVs on close binaries. That made people at least stop and ask, do we have the ability to make this statement firmly yet? But once transits came along, especially Kepler, then we saw that there was a much clearer signal that inside of 50 or 100 AU, an auspiciously similar number to what we saw for disks at young ages, then the planet currents are suppressed by a factor of 3 or so, not too different from that suppression factor we saw for disks, where disks clear quickly in this separation range. And then outside of that range, then it looks like maybe it's actually not that different between what would be expected from a sort of reference population of all field stars and their binaries, which is the blue curve here, versus what is actually seen. But if you modify it by just saying get rid of 2/3 of the close binaries out of the planet sample, or say they fell out, those 2/3 fell out because they got rid of their planets in some way, then you can actually match up with what's observed for Kepler surprisingly well. And a lot of people have now been able to confirm this across a wide range of samples and different mass ranges, like just for M dwarfs, specifically across Kepler, K2, TESS, et cetera. But once you get outside of that interstellar system, then in broad demographics, at least in terms of occurrence rates, it actually doesn't seem to change that much. And so there doesn't seem to be a large suppression factor. We've got binaries at separations of hundreds to thousands of AU. This was seen fairly early on in Kepler samples, and then expanded out through full Kepler samples and the beginnings of test-based samples, and for nearby M-dwarf samples as well. I think I keep on hitting the forward button instead of the pointer. And so it seems like once you're outside of sort of tens of AU, out to hundreds and thousands of AU, you've got the planets. Of course, there's still questions of what kinds of planets are there more subtle influences? And so with this picture in hand of maybe bad things happen close in, but nothing's too extreme farther out, it's worth asking what are some questions that we need to be looking at in order to take this to the next level and ask not just, are there planets, yes or no? Binary questions, haha, are simple, but we want to get past it. But we can ask, what kind of planets do you get? What are their configurations, their architectures, orientations? And so, for example, we can ask, do binaries make different planets? So this is a very recent result from Tyndall Sullivan, where they showed that if you have close binaries inside of 100 AU, then you get a different radius distribution than for wide binaries, where for close binaries, then there are plenty of super-Earths, but not so many sub-Neptunes. It seems to tail off pretty quickly once you get up above the super-Earth regime. Whereas for wider binaries, then the distribution between that versus the overall distribution for Kepler is not actually that different, albeit with questions about do you see the radius gap or not. And so this raises the interesting idea, if you have a close binary there, even if you do get planets, but then also maybe you can ask some questions about a little further out, then you're probably tidally truncating the disk at early times when you were building the planets. And so this probably is changing the mass budget. Is it going to change the mix of ingredients? So for example, if you truncate at 1/3 of the binary semi-major axis, as is canonically assumed, you're going to start truncating ice lines. And if you don't have any material outside of an ice line, you won't have solid phase ices to go into your planets, so you won't be able to build icy planets. Or they'll have a different mix of ices. And so this is interesting to look at and ask, can we turn this into a route toward controlled experiments in planet formation where you can look at a binary and say, I see the orbit now. It hasn't changed since an age of 1 million years. So I can predict, going back, what the effect would have been on the planet-forming environment and turn that knob and then say, did I get different planets out of it? Turn the knob in various ways, get different planets, and maybe we get a handle on the planet formation physics that is otherwise really hard to connect from ages of 1 million years to 5 good years for the same planets coming out of the same disk. course, as we heard yesterday, then it's also very interesting to ask, do both stars form planets? Do they form preferentially around the primary or the secondary? This gets back to those questions of where does the mass even accrete to? How big of a disk do you get around the primary or the secondary, with questions around what is the specific angular momentum of the material coming in. If it's higher angular momentum, then it'll take longer to get down to the bottom of the potential well, so it's easier to route it toward the wide secondary, lower mass secondary that's like higher up the potential well. If it's low angular momentum, maybe it'll go in relatively quickly and go straight down to the primary star. And so this sets up an interesting comparison point back to what would have been happening at early times that we can then look at in class 1 protostars and ask, what is the angular momentum of envelopes? Does it differ between binaries and single stars? And so if we can identify samples where we can say this planet is ambiguously around the primary or the secondary, as Nathaniel told you yesterday, it's harder to say unambiguously around the secondary, but we can see cases of unambiguous circumbinary planets. Then you can start to set up this question and get back at those mass budgets and accretion histories. A different angle you can take is to ask not necessarily like what kind of planets are you getting or where are they at, but what is the overall architecture of the system and how are things oriented with respect to each other? We have a lot of angular momentum vectors to think about in binary systems. There's each of the stars, there's the binary orbit, there's each planet orbit. And we can ask, should these be aligned with each other, should they not? There are complicated questions of, do they evolve to alignment or evolve out of alignment? But we can start to see trends in the planet samples and then go back to compare them to early times and say that, for example, it looks like when the binary companion's relatively close in, not tens of AU, but inside of something like 700 AU, as Dupuy et al. 2022 and Sam Christian have shown in 2022 and 2024, inside 700 AU, then the orbits tend to be, if not strictly aligned, then at least correlated. There might be differences of like 10 or 20 degrees, but not 90 degrees for the most part, between the binary orbit and the planet orbit. This is an easier measurement to make for transient planet systems because you know the planet is edge on. Once you get outside of that, then it starts to be more randomized. And so I think this sets up an interesting question. Some of the planets and the binaries know about each other for whatever that might mean in detail. On scales of hundreds of AU, we haven't really been able to probe tens of AU so much yet. And so I think it sets up this interesting question. Is this going to matter for the survival of the planets? Do planets preferentially survive if you can like keep it strictly aligned? And even, whereas here, out at hundreds of AU, you get alignment within tens of degrees, which is going to start to be dynamically more important once you make the whole system smaller. And so getting more alignment measurements for very close binaries, I think will be an interesting route going forward. But we also want to think about catching the physics in action. And so this is a very new result from Madison Barber, a graduate student at UNC, where Madison found that there's a transient planet in the Taurus star forming region. 3 million-year-old transient planet is already intrinsically very, very cool. But it turns out that it's a transient planet in a system that has a protoplanetary disk, which should immediately make you stop and say, wait, why or how? Because if you have planets form out of disks, we kind of assume they're all aligned because the planet formed out of the disk. If the disk is seen, or if the planet's edge on, presumably the disk would be edge on and would block the view of the planet. And here, the answer is this is actually a case of misalignment between the disk and the planet. So it has a transient planet that's edge on. The rotation of the star is edge on. There's a disk that's inclined by 60 degrees. There's also a wide binary companion a few hundred AU away that's also edge on. So it's aligned with the star and the planet, but not the outer disk. And that bothered me because once I saw the wide binary, I was like, oh, sure, that's torquing the outer disk out of alignment. It won't be aligned with the inner system. It'll be aligned with the outer system or on its own vector. But no, everything's aligned except the outer disk. I don't really understand that, I will say. But as we find more of these systems, there are 5, maybe closer to 10 young systems in binaries now. We can start looking at them and say we've taught them in the middle of the physics. Can we model what already happened and what will happen from here to start building bridges from early times to late times? What will this look like in the future? So those are some of the opportunities, but there are also still things that we need to think about going forward that I'll go over in my last 5 or 6 minutes of this talk. And I'll say, for one thing, we really need to be thinking about sample biases. This is not the most exciting thing to talk about, so I will move through the slides quickly. But it's going to be important because we are counting things, and if there are biases in whether things got into the sample in the first place or whether we found planets around them, then we're going to count the wrong numbers. And so, for example, one that's not particularly exciting but important is the Kepler sample was Malmquist biased. It was selected pre-Gaia, and so all they had were photometry from the Kepler input catalog that they fit to say what the stellar properties were, including a distance. And then they started selecting things. And you can actually show, if you take kicked photometry and compare it back to modern photometry, specifically for binaries where you know the contrast and you can solve out for what the primary star brightness is alone, you can show binaries that are close in and equal brightness tend to be over-luminous in the kick compared to their true brightness because they are binary systems and they didn't know that there was extra flux being added. So they're overrepresented, you need to downweight them in your sample. There's also another bias going in the opposite direction for binaries though, which is that when they were selecting the Kepler target sample, they were specifically trying to identify bright neighbors that would dilute away the Earths and get rid of them because they were trying to find Earths. They wanted to measure A to Earth. And so by rejecting all of the stars where they could see there was a bright nearby star, they basically introduced a bias against all of the binaries on separations wider than an arc second or two, out to basically the size of the photometric aperture. You actually see this, maybe riffing back to a question that was asked earlier in the week. If you look at the contrast versus the separation for all of the Gaia neighbors to non-Kepler targets and Kepler targets, and the brightness ranges of like KP mag of 12 to 13 or 13 to 14. Basically, all of the non-targets are binaries that fall in that range. Brighter than KP mag of 14, if something wasn't observed, it was probably because it's a binary. Otherwise, it almost certainly got into the sample. Below that, things get messier. We can turn this into a selection fraction and say that the selection fraction at a few arc seconds and similar brightness is basically 0. You actually see that in some of the other plots I showed. And then you can correct for this at least. But you need to know to correct for this, or else you'll end up with wonky separation, semi-major axis distributions, and potentially wonky binary frequencies. And so I've turned both of these into basically a correction map, where there's a range at a few thousand AU where the correction factor is like 0.6 or 0.7. You lost a bunch. And there's a range close in where Malmquist bias meant you basically got more than twice as many binaries as you expected. So you can correct for this, you just have to know to build it into your demographic calculations. I'll note we also need to build larger samples. And so the way we've been doing this, well, I should say most of our surveys up until now have been target sample sizes of like 100 or a few hundred stars. If we want to start dicing all in extra parameters, we get to thousands. And so the way to do this is to hopefully make things more efficient because observing thousands of stars will take a lot of resources. And so the way that we've been doing this is using Gaia's RUWE, RUE, people say. I'm fighting the good fight, but I think I'm going to lose. But the idea is that this is a measure of the excess astrometric error in Gaia data. A well-behaved star has a RUE of 1, reduced chi-squared, call it. If it has a high reduced chi-squared, a high RUE, then it is probably a binary. These are actually visual binaries where they're being misfit because they're being fit with 1 PSF, not 2, in the Gaia pipeline. But you can show for single stars, and these are verified single stars from high-resolution imaging, then it really does center very nicely at 1. But you can then say if it's above 1, you can actually map out with known binaries and say if it sits here, it's going to be 1.5. If it sits here, it should be 2.5. Up in here, all of these are the things that actually drop out of the Gaia catalog because they don't have an astrometric solution. The data was too bad for them to fit. If it doesn't have a parallax, it turns out it's a binary. So that's going to be another bias in all our samples if we don't correct for that, ironically. And so we can actually use this in order to say 85% of our targets don't need to be observed anymore because they have normal Gaia errors. You can draw a contrast curve here that's very competitive with 8 to 10 meter class telescopes with speckle or non-rhodant aperture masking or other techniques. And you can say if we don't see excess errors in Gaia, then we're not going to see anything if we observe this with high resolution imaging. So we don't need to. Just adopt this contrast curve and then observe the other 15% where there's actually something there to see and figure out exactly where it's at. And so we've done this and basically built our entire sample up to about 2,500. Basically all of the KOIs out to about 1.2 kiloparsecs can now be built into our demographic samples. And it probably should be applied much more widely than that. I figured I wouldn't have time, so I'm not going to get into the topic of dealing with all the chance alignments. It's more mechanical than interesting, so it's fine that I'm skipping past it. But we basically are at the point where we can say there are about 600 of like confirmed binary companions, highly likely binary companions, I should say. Another 150 to 200 that need more follow-up, and all the rest we can disregard out of this complete set of observations for coupler. And we're finding interesting things. For example, as we're able to go to wide systems, because now we're able to use Gaia to confirm stuff, then we're finding there's an excess of very wide systems that I'm still wrapping my head around. I'll say I don't think this is a binary effect, because I don't see why having a binary companion at 5,000 AU would make planet formation like more efficient. I suspect this is an environmental effect. You only have a binary companion survive at 1,000s of AU. It forms in a very low density quiescent environment. No flybys, no nearby O stars, et cetera. And those are probably the same things that make your protoplanetary disk last longer and stay more massive so that you can build bigger planets. And so the last point I want to end on is to point out that interesting opportunities await in terms of the astrophysics, but the binaries are awaiting you in your surveys as well. And so we really need to be thinking about, going forward, understanding not just what is the astrophysics going on here, but predictively, where should we be expecting to find planets when we're doing things like planning HWO? Because all of these stars in the solar neighborhood are also going to be the tier 1 and tier 2 stars for tier A and tier B for HWO, and a whole lot of our binaries. Alpha Cyn A and B, Eta Cas is right here. I think Eta Cas is tier A, Alpha Cyn is tier B, but it's going to get observed anyway, of course. And they're going to matter for all of these missions that I was going to list, and then I realized the organizers did it in tomorrow's schedule, so I just included it here. And so we need to be thinking about, can we say some of these don't have planets, or they definitely have planets? And with that, since I'm over time by a little bit, I will put up some takeaway points for you, and then I'd be happy to take questions. Thank you.
Great, we got questions for Adam. Where the mic runners? Here we go. Right here.
I'm gonna get out of the spotlight so you can see who's asking questions.
Hi, Songhu Wang, Indiana University. Based on your observations, do binaries make hot Jupiters?
That is a good question. The statistics I've seen have been a little, there have been enough claims in both directions that I feel like I still need to sit down and sort through that question more myself. I feel like there are enough routes to drive high eccentricity migration with other planets in the system, for example. I don't think you need a binary. There are observational surveys showing there are plenty of hot Jupiter systems that don't have a wide binary companion at least. And so they can, I don't think they're needed. Whether they are actively hostile to it for any separation ranges, I think is an open question. Most of our samples aren't large enough to pick out just a hot Jupiter sample. Maybe that'll change now that TESS is yielding its complete samples, as we've heard. Okay. Zoom.
Hey, Aman Carr, Georgia State. Question on your Ruby slide. You said if it's less than 1.2, you can assume most of the binaries have been taken out, but what do you do with equalized binaries where they have no astrometry perturbation? So your Ruby is going to be low anyway.
So this is a good place for me to back up a little more and say a little more about the technical details. Most of the time, what you're seeing with high Gaia errors is not true astrometric motion that's not being fit. It's that you have two stars there that are marginally or completely resolved on the Gaia spacecraft, but the pipeline is fitting one PSF to them. And so because Gaia is doing basically a bunch of 1D stands, as you stand in different directions, you project those two stars differently. So you end up fitting that one star model differently, depending on if they're like this and like widely separated, or you stand like this for a binary that's like this, and they're like not really resolved along the stand direction. So it's all errors in terms of not fitting the 1D stands with a two-source model. And then equal brightness binaries are actually worst. Equal brightness 0.3 arcsecond binaries basically never have a parallax because they just break the Gaia pipeline too badly.
Oh, I'll run first.
From online, You referred to a viscous time for df tau of only a few thousand years, yet molecular viscosities imply disks should live for about 1 gigayear. Did you mean that gravitationally mediated torques are responsible for the evolution of df tau disks and not viscosity?
I'll say that's probably a better question to address to Taylor Tutra, who was the lead author of that paper. But keep in mind that disks are truncated at something like a third of the semi-major answers of the binary with arguments. And so the mass reservoir you have, basically this is only an inner disk that's truncated there at something like 3 or 4 AU. So there's not a lot of mass there, and the timescales in the inner disk are pretty fast. And so the small amount of mass that's there should go ahead and accrete down to the star pretty quickly. And in a single star, it would be replaced by the outer disk. But there is, at the very least, any outer disk is outside of the binary and very far away. We can't really detect it yet. So it's not even clear to me how much mass there is outside of the binary. There's got to be some, or else I think the disk would have gone away by now.
Unfortunately, that's all the time we have for questions, so we'll have to move on to the next speaker. Thank you very much. Speaker.